Hey guys, what's up? This is Madan here, and I have brought another video for 12th class students. Might be useful for 11th class also. And this is from the next topic, which I started doing from haloalkanes and haloarenes. But in case I need to remind you, I did a couple of topics from haloalkanes and haloarenes. There was like classification, there was nomenclature, there was preparation. Now this part is going to be about physical properties of the haloalkanes and haloarenes, right? So let's try to get it through, because this will definitely going to be very, very important for you. Why important? Let me tell you. I was thinking I will let you know once the video is about to end, but I've changed my mind. It's important because almost every chapter organic chemistry has this kind of physical property to study. And most of the time, the physical properties are based on the similar factor. So once you understand the physical properties of the haloalkanes and haloarenes, it's going to get you real good help out there when you study the physical properties of other compounds from the organic chemistry in the coming chapter, right? So let's start. I've divided all the physical properties in some section. Let's start. The first one is with color of the haloalkanes. You know what? Most of the time, or almost all the time, the haloalkanes are colorless. The haloalkanes are colorless when they are without impurities. They do not have impurities. So if they do not have impurities, they are going to be colorless. So one thing is also coming out to be very, very clear, that they are going to be colored. They are going to be colored in colored when they contain impurities. They contain impurities. So I hope this has helped you to get through the color of the haloalkanes, which I just said. They are usually colorless, but if they have some impurity, they might appear colorful as well. Let's talk about the second properties, which is physical state. Physical state. I'm dividing the physical state in some of the part. The lower haloalkanes, up to 2 carbon, are gaseous. Want to know the reason? Because smaller the number of carbon smaller will be forces of attraction, van der Waal forces of attraction. Van der Waal forces of attraction. Right? So smaller the molecule, smaller will be the mass, and smaller will be the van der Waal force of attraction. So if the van der Waal force of attraction they are small, they are going to be gaseous. So let me underline here so that you understand. Up to 2 carbon, the haloalkanes are in gaseous form. Okay. Now let's talk about the second party. Haloalkanes or other derivatives with more than 2 carbon uh, they are liquid or gases. Liquid or solid, sir. Liquid or solid. Let's get back to the reason again. As the number of carbon will be small, van der Waals force of attraction is going to be small, but with the increase in the number of carbon, this very same force is going to be higher, and that's why they will either become liquid or become solid. So initial, 4 or 5 members after 2, they will be liquid, and all higher members with more than 10, 12 and all, they are going to be, solid. So let me write here, carbon 1 to carbon 2, they are gases. Then carbon 3 to carbon 5 or 6 maybe, they are liquid. And carbon 7 to onwards, 7 or more, going to be solid. Now the reason is simple, because van der Waals force of attraction increases. I'm writing here, van der Waals forces increases, increases down the group. Okay, so this is about the physical state of the, haloalkanes and haloarenes. So the third properties I am talking is about density. Haloalkanes density increases down the halogen group. What that means? That chloromethane will have least density, then it will have chloroethane, then it will have bromomethane, and then if you take another example like iodomethane, so what is happening here? There it is chlorine, there it is bromine, there it is iodine. So if you remember, in the periodic table, the iodine is towards the downward region, while chlorine and fluorine are at the upper region. So down the group, what happened? The mass increases, and due to increase in the mass, the density also increases. So you can compare any other compound based on the masses of the halogen being provided. So the final conclusion is coming out to be the density of the haloalkanes increases down the group based on the number of halogen atom and type of halogen atom. The third, was it third or it was third probably. So let's talk about the fourth one. What fourth one is? Fourth one is about boiling point. So this is going to be something very important, boiling point. Okay, so boiling point, what happened? With increase in number of carbon, not only the mass increases, but also van der Waals forces increases. And you need to remember that if the force of attraction between the molecules increases, definitely the boiling point is going to be more and more. So let's take example. Suppose, you're talking about, like chloromethane chloromethane, talk about chlorobutane, and let's talk about chlorohexane. Chlorohexane. So what we see out here, that hexane has 6 carbon, the butane has 4 carbon, and the methane has only 1 carbon. So it's very simple, because the number of carbon here is highest, therefore the boiling point for this one will be highest, and this one will be second highest, while this one will have the least, boiling point. Boiling point depends on so many factors. So let's get through the next part here. So boiling points depends on other factors as well. Boiling points. Haloalkanes have higher boiling point, higher melting and boiling point than alkanes of comparable masses. What that mean here? Let's talk about iodomethane or like iodobutane, right? And then talk about butane. So what is happening here? In the iodobutane, the structure is going to be something like this. This is iodobutane and this is your butane. So this is a non-polar compound. You need to understand that butanes are non-polar. Why non-polar? Because electronic distributions are everywhere the same. But what's right here? The electron density is towards, iodine. Therefore, this one has a partial negative charge and this one has a partial positive charge. So these compounds are called polar. So because haloalkanes are polar, but the alkanes are non-polar, definitely the intermolecular attraction, the intermolecular attraction between the haloalkanes are going to be higher as compared to the intermolecular forces between the alkane. If the force of attraction are higher, definitely the boiling point is also going to be higher. So this one has a higher boiling point, higher BP, and this one has lower BP. Right? So this is the boiling point, trend based on the polarity of the compound with the comparable masses. Let's take another part of the same, and that is what is the effect of branching. Let me introduce. Meanwhile, you can copy. Actually, the third factor that decides the boiling point of haloalkane is the branching in the carbon chain. And I will tell you, after that I will be coming to the writing part here, that increase in the number of carbon branches not only increases the branching but also decreases the van der Waals force of attraction. So what that means? If the branching is increasing, force of attraction is decreasing, and so is the boiling point also. So let's get through that. So effect of branching, that is what the topic is, branching in the carbon chain. Now what I said increase in branching decreases the boiling point. So let's write it first. Increase in branching decreases the boiling point. let's get to know why this is. Because with decrease in the because with increase in the branching, surface area decreases. Surface area decreases, which decreases the van der Waal forces between the molecules. So let me repeat back here. I might be writing, but you have to understand as well, because explaining is more important than just writing over the board. So what I have written here, that if number of carbon remain constant and the branches are increasing, what happened with the increase in the branching? The molecules start becoming smaller and smaller, and because the molecules are getting smaller, the surface area is getting smaller, and if the surface area is getting smaller, the intermolecular force of attraction will also be decreasing, and if the attractive force is decreasing, definitely the boiling point will also decrease. So let's take an example here so that you get to know. Suppose I am talking about chloropentane here, and I am talking about this 2-methyl chloropentane, right? And take another one here. This is 2,2-dimethyl chloropropane. IUPAC name will be something else. I hope you have understand that. But what is the purpose of the topic is here, that right here the branching is most branched. If it is most branched, least surface area. And this one is no branch, so most surface area. And as I said earlier, increase in the surface area increases the boiling point. What that means? Decrease in the surface area decreases the boiling point. So there it has the least boiling point and it has the highest boiling point. And of course this will have medium. I'm not writing, you understand that. So boiling point depends on all these factors. I think this has all gone way more than 20-25 minutes. So there are two things I need to still be discussing from the physical property, and I will make that in the next video in a short while. So with that, in case I'm winding here and you are if you are watching done watching that, I would say thanks for watching, and must watch the remaining part of the physical properties, because I'll be doing that part in the next video. Right? That's it. Thanks for watching.